After completing the content associated with this learning objective, the learner will know the background development of satellite navigation systems, know the various GNSS, Global Navigation Satellite Systems, in operation, their differences and their status, know the importance of a standard datum and describe those used by the main systems, know the limitations of datum systems and resultant inaccuracies and corrections. Since the early 1960s, both the US Air Force and the US Navy had actively pursued the idea that navigation and positioning could be performed using RF signals transmitted from space vehicles. The impetus for development of a space-based system was created by the desire for a global, highly accurate positioning and navigation system that could meet the needs of a broad spectrum of users. The US Navy had sponsored 2 navigation satellite programs, Transit and Timation. Transit, also known as the Navy Navigation Satellite System, became operational in 1964 and was made available to non-military users in 1967. During the same period, the US Air Force worked on another system called System 621B. The US Secretary of Defense issued in 1973 a memorandum telling the Air Force and the Navy to cooperate on the development of a generally acceptable, comprehensive and cohesive all-weather navigation system. The new system was named Navstar Global Positioning System and based on the best features of the previous navigation satellite concepts. The development of the Navstar GPS was divided into 3 major phases. GPS was originally designed and built for military applications by the U.S. Department of Defense. By presidential proclamation, Ronald Reagan declared in the early 1980s that GPS would be made available to everyone, with the exception that the best accuracy would still be reserved for the military. GPS is operated by the United States Air Force. GPS is today the most commonly used navigation system in the world, whether navigation is executed on land, at sea, or in the air. The reliability, position accuracy, user-friendliness, low price of receivers, together with free use of the satellite signals, have made the GPS extremely important to the world economy. A surprising number of different systems already have GPS as a shared dependency, so a failure of the GPS signal could cause the simultaneous failure of many services that are probably expected to be independent of each other. The European Commission has estimated that €800 billion of the gross domestic product in the European Union is dependent on satellite radio navigation. Global Navigation Satellite Systems is the generic term for space-based systems that transmit signals that can be used to provide 3 services: position, navigation, and timing, known collectively as PNT. The best known and most used is the US Global Positioning System, although the Russian GLONASS system is regaining its strength, and other systems are being developed, most notably Galileo in Europe and Compass in China. The systems all work in approximately the same way, so this module will focus on a description of GPS. One of the biggest benefits over previous land-based navigation systems is that GNSS works in almost all weather conditions. However, there is a growing concern that it is becoming more and more the only electronic navigation system available for use on board ship. Surprisingly, the transmitter power from the satellites is only about 100 watts, which has to spread out to cover about 38% of the Earth's surface. Needless to say, it is relatively weak when arriving at the Earth's surface, and open to interference, jamming, and spoofing. Since GPS uses time measurement parameters to provide positioning information, accurate timing is an essential part of the system. It might be interesting to know that each satellite has 4 incredibly precise atomic clocks on board. Atomic clocks don't run on atomic energy. They get the name because they use the oscillations of a particular atom as their metronome. The Earth is fairly spherical, with a mean diameter of 12,742 kilometers, but not precisely, and should better be considered as a spheroid or ellipsoid, slightly flattened at the poles and bulging at the equator. This representation is accurate within a few hundred meters, and nowadays readily assessed by accurate observations of Earth from space. Previously, we have been able to agree on regional projections and datum, but very accurate satellite-derived global positions have introduced a need to be more precise when we convert from this spheroid to a two-dimensional chart. It is not a simple problem, because if mean sea level is used to measure heights and depths, this itself varies globally by hundreds of meters due to tides, weather, air pressure, gravity effects, etc. Even parts of the Earth's surface are shifting relative to each other due to tectonic plate movement. However, it is essential to have a standard datum or surface to which all measurements can be referenced, and this is defined by the World Geodetic System, the latest version being WGS 84, which has been revised several times. WGS 84 is the Global Coordinate System, datum, which is used by GPS, and though GLONASS uses another datum, known as PZ90, this is closely aligned to WGS 84. Conversion between coordinate systems requires complex mathematical transformations. The navigator should always be aware of which coordinate/datum system is used by the paper and electronic chart, and make necessary corrections when needed. Irrespective of the datum of the chart in use, it is always advised to operate the GPS in WGS 84 and apply any corrections to the output as necessary. These corrections are normally written on the chart. Remember that many of today's navigational paper charts and raster charts are not produced in WGS 84, but approved vector charts will always be WGS 84. All British Admiralty charts are now compatible with WGS 84 datum.